I'd like to briefly talk about both the Arrhenius equation and the Clausius-Clapeyron, the vapor pressure equation, because they're essentially the same equation. These are a little bit harder to use, but if you learn how to use it, it's really not too bad. Ln K1 over K2 over K1 equals EA over R 1 over T1 minus 1 over T2 versus ln P2 over P1 equals, I'm going to actually switch this around because it's just so they're exactly the same, delta H over R 1 over T1 minus 1 over T2. That these two equations look at the relationship of temperature and some constant. The temperature relates to the vapor pressure based on the pressure boiling. Well, the temperature relates to the vapor pressure based on the enthalpy of vaporization. And the temperature relates to our rate constant based on the activation energy. Both of them are divided by R, which is 8.314. So these guys are really essentially almost the exact same equation. It's really neat in a way. But given this, if I have a activation energy of, say, activation energy of 120 kilojoules, and it's like, and our K1 is 12.2 at 25 degrees. What temperature would it take to get to, say, 36.6? So what temperature would it take to get to 36.6? So how much would it take to triple? How much would it take to triple the temperature? I mean, how much would it take to triple the rate constant? So ln 36.6 over 12.2 is going to be ln of 3 equals, you got to watch out the units, 120,000 over 8.314, 1 over 298 minus 1 over T2. So 120,000 divided by 8.314 is 14433.5. So I'm starting by evaluating some of this stuff. ln 3, I can find that number. Then I'm going to divide both sides by my 14433.5. I'm going to get a really small number. So when I do this, I'm going to get 0.00004076115 equals 1 over 298 minus 1 over T2. So getting my T2 to the other side, 1 over T2 equals 1 over 298 minus our thing. So I'm going to make that negative and add that to 1 over 298. And I do that, I get a much less small number. But on these type of problems, you do not want to round too much. And now to get this, since this is 1 over T2, I can invert this. Take that to the negative first power, take that to the negative first power, and that's going to get us our answer in Kelvin. So the temperature would have to be 304 Kelvin. To triple the rate constant, we have gone up to we've gone up by 6.9 degrees. Gone up by 6.9 degrees under this situation to triple it. So the same thing would hold true if I was asking the vapor pressure. It doesn't matter the units of the vapor pressure units will be the same. They can cancel out without any problem. I'll do one more problem like this just to show you like what happens if I weren't given the pressures. What happens if I wasn't given the pressures? So let's say the delta H vaporization was 235 kilojoules, and the P vape 1 was 85 torr at 25 degrees C. What is the P vape 2 at 50 degrees C? So plugging in ln P2 over 85 equals, we have 235,000 over 8.314, and we have to do this in Kelvin. 1 over 298 minus 1 over 98 plus 20, 1 over 323. So let's start by evaluating that. 1 over 298 minus 1 over 323 times my 235,000 divided by 8.314. Evaluating that, we get 7.3414 equals ln P2 over 85. So the next step, inverse log both sides. Inverse log. And then I get a big number, and then I go times 85. So in this case, my numbers are kind of outrageous. If I did that, I'd have 131,144 torr under these conditions. I'm guessing my vapor pressure is a little too high, or my enthalpy of vaporization is maybe a little too high. Well, say la vie. Or maybe say la vie, either way. But okay, we got a very big number.